So hello everyone again. This is lecture 2 part 3 of dual nature of radiation and matter. Let's go on with the further discussions of experimental study of photoelectric effect only. So I am Sameer Lavankar. Let's begin our discussion. Okay, so right now we are on the fourth point, that is experimental study of photoelectric effect. In this in the previous discussion we already completed with the effect of potential on the photoelectric effect or on the photoelectric current. Today we will start with the second point, that is the effect of frequency on the photoelectric effect. Okay. So, let us not waste any time. Till now these 3 points are being completed, we are basically on the fourth point now. So, this is basically your effect of frequency of incident radiation on stopping potential. So, this diagram is being same only. We will today try to understand what is happening in this sequence here. Okay. So, first of all let me start reading only. Let me iterate it carefully. So, we will now study the relation between the frequency nu of the incident radiation and the stopping potential V naught. Okay. In the previous discussion what we understood is what is the relation between the intensity of the incident radiation and the stopping potential V naught. Today we will try to understand the relation between the incident frequency and the frequency of the incident radiation and the stopping potential V naught. Okay. So, now we suitably adjust the same intensity of light radiation at various frequencies and study the variation of photocurrent with collector plate potential. Okay. So, we try to please remember here now the intensity is same, only the frequencies are being varied. Okay. And we try to study the variation as shown in the figure below. Okay. So, everything is same, only we try to change the frequency. The resulting variation is shown in the figure below. So, this is the resulting variation. As you can see, this V3, V2, V1 are basically different frequencies. Okay. So, we obtain different values of stopping potential, but the same value of the saturation current for incident radiation of different frequencies. Okay. So, as you can see, saturation current is same, but for different frequencies the value of retarding potential is different. Okay. Let me just redefine again what is saturation current. So, saturation current is the maximum current which is obtained in the electric circuit of photoelectric effect when we try to increase the potential upon irradiation of the light on the metal surface. Okay. What is retarding potential? When we try to reverse the polarity, then that minimum negative potential such that the electric current or the photoelectric current emitting is 0, then our photoelectric current is 0, then that potential is called as your retarding potential. Okay. So, when we tried to, in the previous discussion what was happening is, with the increase in the intensity the saturation current was increasing, but the retarding potential was same for the different amount of intensities of radiation, keeping the frequency constant. Now, in this discussion what is happening is, the saturation current is constant for the different variations of frequencies, but the value of retarding potential is different for the different what we can say frequencies. Okay. For more higher frequencies, the more negative the retarding potential goes. Okay. So, that thing is only been written here. So, the energy of the emitted electrons depends on the frequencies of the incident radiation. The stopping potential is more negative for higher frequencies of incident radiation. Okay. The stopping potential is more negative, as you can see the stopping potential is more negative for higher frequencies of incident radiation. In the figure below, the stopping potential are in the order VO3 greater than VO2 greater than VO1, as you can see, if the frequencies are in the order V3 greater than V2 greater than V1. So, magnitude wise the V3 will be greater only, but if we go in negative sequences, then the potential will be lower for V3. Okay. So, as V3 greater than V2 greater than V1, therefore, VO3 greater than VO2 greater than VO1. Okay. Let us move on. So, nu small is basically frequency and greater is basically potential. This implies that greater the frequency of incident radiation, greater is the maximum kinetic energy of the photoelectrons. Okay. Consequently, we need greater retarding potential to stop them completely. Quite evident, because if the kinetic energy, if the energy of that thing is more, then that the amount of push required, or let us say to stop something, is more, because more energy requires more amount of force to stop it. Similarly, it is given here that as the frequency increases, the kinetic energy increases, and as the kinetic energy increases, the amount of retarding potential required to make it to stop, or let us say for the electron stop, is basically higher. So consequently we need greater retarding potential, to stop them completely. If we plot a graph between the frequency of incident radiation and the corresponding stopping potential, so it is frequency of incident radiation and the stopping potential for different metals, we get a straight line. So as you can see, we get a straight line as shown in the above figure. Okay. The graph shows that the stopping potential V naught varies linearly with the frequency of incident radiation for a given photosensitive material. So it is always linear only, that thing is first point. Second point is very important. The second point states that there exists a certain minimum cutoff frequency nu naught. There exists a certain cutoff minimum frequency nu naught for which the stopping potential is 0. So till this point for every of the sequences the stopping potential is 0 only. After a particular value of this it tries to increase linearly, okay, and this is only thing which is called as your threshold frequency. So these observations are two implications. So what are the two implications? For the first is that the maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation, quite evident as it is written, but is independent of its intensity. Okay. So when the stopping potential varies with the intensity of frequency, then the intensity is independent. It does not depend on intensity also. If we try to change the intensity also, the graph remains same. Second is that for a frequency nu of incident radiation lower than the cutoff frequency, let us say this for this metal and this for this metal, no photoelectric emission is possible even if the intensity is large. So even if you try to increase the intensity to very much higher, if you try to keep the source very much near, then also there is no change as long as that frequency is being matched, that threshold frequency is being matched. Okay. This minimum cutoff frequency nu naught is called as your threshold frequency. Okay. So this thing was also been explained in the previous last lecture discussions, lecture 1 discussion, again it is being explained here. Okay. So this minimum cutoff frequency nu naught is called as the threshold frequency. It is different for different metals, quite evident it is different for different metals. Different photosensitive materials respond differently to light, as you can see. For metal A, this is the graph, for metal B, this is the graph. So as you can see, for different metals the graph is different, that is it is sensitive differently with respect to ultraviolet light or let us say visible light being impacted upon. So different photosensitive materials respond differently to light. Selenium is more sensitive than zinc or copper. So this is just for theoretical part, you may remember also selenium is much more sensitive. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives different response to light of different wavelengths. Okay. So if you try to change the wavelength also, then also sometimes some photosensitive substances may not give result and sometime may give result. Okay. So that thing explained, and now I think this is the last concept of this thing. So for example, ultraviolet light. So now just to explain what is happening in this last discussion here. For example, ultraviolet light gives rise to photoelectric effect in copper, while red or green light does not. Okay. So what is red or green light? They are basically visible light. So for copper, the photoelectric current or photoelectric effect only and only visible when the wavelength of light is in the range of ultraviolet light. If it is in the range of this visible light, then the photoelectric current is or photoelectric effect is not visible. Okay. So that is only being said that different materials perform differently, behave differently. Note that in all the above experiments, it is found that if frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously without any apparent time lag, okay, even if the incident radiation is very dim. So these are just the experimental formulation which were being explained. So we found that there was no time lag. No time lag is in even if the incident radiation is very dim, very less also, then also the photoelectric effect was visible. Okay. It is now known that emission starts in a time of the order 10 to the power minus 9 seconds or less, that is 1 nanosecond. So this is very short time frame only. Okay. As you can see, 1 upon 10 to the power 9 times of a second is basically what is 1 nanosecond. Okay. So you can understand from this sequences only that it is very less time, that time lag is very small. Okay. So now we try to summarize everything what we understood till now. So we now summarize the experimental features and observation described in this section. In this section, as in this section in which the concept of a variation of the frequency is being dealt. Okay. So for a given photosensitive material and frequency of incident radiation above the threshold frequency, it is being given that the frequency should be above the threshold frequency. the photoelectric current is directly proportional to the intensity of incident light. Okay, the current is directly proportional. So even if just to remember it also, you can just write it as I is directly proportional to I. One is your current, one is your intensity. Fine. So what you can say that photoelectric current is directly proportional to the intensity of incident radiation. Next is, for a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity. Okay. So now what we try to do, here the frequency is being kept constant. When the frequency is being kept constant, saturation current varies for the intensity portion, but it is constant value of retarding potential. If we try to change the value of frequency and keep the intensity constant, then the saturation current is independent, but the retarding potential keeps on varying with the increase in the potential towards the negative side with the increase in frequency. Okay. So for a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity. The first point which we understood in this experimental study. Second is, for a given photosensitive material, there exists certain minimum cutoff frequency of the incident radiation called the threshold frequency. This threshold frequency has been explained many times to you, below which no emission of photoelectrons takes place, no matter how intense the incident light is. Okay. Above the threshold frequency, the stopping potential or equivalent to the maximum kinetic energy of the emitted photoelectrons increases linearly with the frequency of the incident radiation, but is independent of its intensity. Okay, so even if the intensity is very dim, then also this thing can be explained as long as it is in the range of, or it is greater than this threshold frequency. Before this, even if you try to increase the intensity to maximum value also, very higher also, then also no photoelectric effect will be visible. Okay. The photoelectric emission, fourth point is, so this thing has also been explained. Next is, the photoelectric emission is an instantaneous process without any apparent time lag, that is 10 to the power minus 9 seconds or less, even when the incident radiation is made exceedingly dim. Okay, so even if it is made exceedingly dim, then also the time lag is very less, and even it does not depend upon the intensity is either dim or higher, the photoelectric effect takes place. Okay. So that was a complete concept of your experimental effects on photoelectric effect. Let's now start with a new concept of the application, or let's say the understanding of wave theory of light in this complete photoelectric concept. Okay. So in the previous discussions of your ray optics, light ray optics, etc., you may have heard as light being explained using Descartes theory also and wave theory also. Descartes theory was basically particle theory, but you may have arrived at a sequence that some particular concept such as diffraction, polarization, etc., can only be understood by wave theory. It cannot be explained by using particle theory. Similar thing was being explained now. So now we will try to understand what is happening in a photoelectric concept also. For some major, let's say smaller, bigger objects, why was a wavelength concept being neglected, or let's say it is not so much necessary, but for very smaller particle it is necessary sequence. Okay. So let's start this discussion today, that is photoelectric effect and the wave theory of light. Okay. So something I need to explain before starting the complete concept. So everything which I just said is being nicely written here. Okay. So the wave nature of light as well was well established by the end of the 19th century. This was the only time at which the discovery of electron was also taking place. The phenomena of interference, diffraction and polarization were explained in a natural and satisfactory way by the wave picture of light. Okay, because this wave picture of light cannot be, this picture of light cannot be explained by using particle theory, that is why wave theory came into picture. And what were the basic things which we understood, or which were made to explain by the wave theory of light? The first was interference, second was your diffraction, third was the polarization. Okay, these all things are being explained very clearly in your concept of wave optics. So you can go and refer to those lectures also. So now next thing is, according to this picture, light is an electromagnetic wave consisting of electric and magnetic fields with continuous distribution of energy over the region of space over which the wave is extended. Okay, what does it try to say? So basically what is happening is, So, let us suppose this is the electromagnetic wave being explained here. Okay, so what is happening basically is that let us suppose this is the electric field and this is the magnetic field. Okay, so and we can say that this is the direction of propagation of light in the, let us say, x direction, the electric field is varying in the y direction and the magnetic field is varying in the z direction. Okay. So, that thing is only been explained here. So, according to this picture, light is an electromagnetic wave consisting of electric field also, as you can see electric field is existing here, and magnetic field also, okay, with continuous distribution of energy over the region of space over which the wave is extended. Okay. So, as you can see there is a continuous distribution, as in the complete wave is being traversing from, let us say, source to the receiver. Okay. Now, let us now see if this wave picture of light can explain the observations on photoelectric emission given in the previous section. Okay, so let me just try to understand that thing now. So, according to the wave picture of light, the free electrons at the surface of the metal over which the beam of radiation falls absorb the radiant energy continuously. So, this is just thing which you need to understand, that what actually wave theory tells you about. It tells that the free electrons at the surface of the metal, at the surface of the metals over which the beam of radiation falls, absorbs the radiant energy continuously. So, it tries to absorb, right, it tries to absorb. Look over to the complete process very carefully, because we will try to understand what is actually happening in photoelectric effect. Okay. So, till now what does it try to say? Let us say this is the metal surface, electrons are being were present at the locations, the incident light was being impacted upon, and then the energy was being absorbed by these surface electrons. Okay. Now, the greater the intensity of radiation, the greater are the amplitude of electric and magnetic fields. Quite evident, the amplitude as in the highest value of this sinusoidal form here. Consequently, the greater the intensity, the greater should be the energy absorbed by each electron. Quite evident, because more intensity, as in more energy is being imparted from the light to the, let us say the emitter plate, and hence more amount of energy can be absorbed by the electrons. Okay. In this picture, the maximum kinetic energy of the photoelectrons on the surface is then expected to increase with increase in intensity. Okay. So, what does it try to say? The maximum kinetic energy of the photoelectron on the surface is then expected to increase with increase in intensity. So, as the intensity increases, the amount of energy absorbed by these metals, by these electrons increases, and therefore, the maximum kinetic energy increases. Okay. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation over sufficient time should be able to impart enough energy of to the electrons, so that they exceed the minimum energy needed to escape from the metal surface. Okay. So, what I try to say is that if the amount of time is being sufficient enough, then what will happen is that at some, let us say the frequency is constant, then there is a sufficient intense beam of radiation. What will happen is that energy will be what we can say being absorbed by these electrons, and there will be a time at which the sufficient energy is such much sufficient that it can move out of the electron, move out of the metal surface. So, that thing has only been explained. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation over sufficient time should be able to impart enough energy to the electrons, so that they exceed the minimum energy needed to escape from the metal surface. Okay. So, let me stop it here only. This is a very good discussion, I need to explain to you further. After this, we will try to understand much more concepts. So, let me stop it here only. In the next lecture, I will start the further discussions. So, the course progress for you, right now we are on the 5th point, that is photoelectric effect and wave theory of light. In the previous lecture we are done with introduction, electron emission, photoelectric effect, and then last in this lecture only experimental study of photoelectric effect is also completed. Okay. So, in the next discussion we will go on with the further discussion of photoelectric effect and wave theory of light, and then we can go to Einstein's photoelectric equation. This is the major part, this is the major numerical part which you need to understand. Then moving on to the particle nature of light, that is what is a photon, wave nature of matter, as in I need to understand you the explanation of why we cannot find out the values of, let us say, two different properties of the material alone, and then finally there will be a division and German experiment. That will be the end of your complete chapter. Okay. So, let me stop it here only. Thank you so much.